All right, in this video, we're going to start the last unit for Calculus AB, which is good news for us. We are rapidly approaching the end. That's good, right? We're all ready to be done, but it's coming soon. But this last unit is going to actually go back, and it's an application of integration. And we could have done it a while ago, but I like to save this one for last, just because some of it's going to get a little bit tricky. But what we're going to be tackling today is not how to find the area bounded by one curve and the x-axis. Today we're going to be looking at, okay, if I've got two different curves, how could I find the area that's bounded in between them? Right? So the area between two curves or between two functions, that's what we're going to be looking at in this video. And the dx integration is probably going to be okay, but the dy integration is going to probably be a little bit challenging for you because we're just not used to doing dy integration. But hopefully by the end of the notes and by the end of this packet, hopefully we'll feel okay. By the way, if you need to, I would definitely pause the video. I would definitely take notes. These are going to be important formulas for us. Right, let's look at the first one. So if we have just this top part, right? If we have this area, we have the top function, which is in green. We have that bottom function, which is in blue. And then if we wanted to find the area of region R, which is the region in between those two functions, how could we do it? Well, we know if we integrated f, it would give us the area bounded by f and the x-axis. And I know if I integrated g, it would give us the area between g and the x-axis. How could I find the area in between the two? Well, what we'll have to do is think about kind of like segment subtraction or sector subtraction or sector addition. If I want to get the area in between the distance, what I need to do is think about, okay, well, what's the distance in between the two, right? Because if I integrate f, that's really the distance from 0 up to f. Or if I integrate g, that's the distance from 0 up to g, right? Integrating a function is really the distance between that thing and the x-axis. But I don't want the area between these functions and the x-axis. I want the area in between them. So I want to know what's that distance in between them. And if we have two curves like this, where one of them is always on the top and the other one is always on the bottom, well, then this distance, I'm going to call it S for now, this distance S between the two curves, that S value is just going to end up being top minus bottom, right? And again, that S value, that's the distance between the two curves. And if I take that distance and if I accumulate it, starting with that first one at A, and the next one, and then the next one, right? And if I accumulate all of those infinitely many slices, each one is top minus bottom, if I accumulate them all the way from the left one at x equals A, all the way to the right one at x equals B, that is how I'm going to get the area between the two. And how we can compile infinitely many things, not just that one slice, not the slice right next to it, right? How can I accumulate and compile infinitely many things? Well, that's what integration is. Right? Integration is adding together infinitely many things. We talked about that back when we did Riemann sums. Now we're doing it really just the area in between two functions. If I am going to do a dx integral, then that means the left side has to be defined by the variable x. So I've got x equals a. Remember, the differential really tells you what variables those limits for the integral are attached to. So if I'm going to integrate from a to b, that means from the left side to the right side, what I need to integrate is the distance in between those two curves, which for us is going to be top minus bottom. Okay, so your dx integration, this right here, that's the general formula. When I'm integrating, and it's in terms of x, I'm going to integrate from the left to the right. That's going to be compiling all those infinitely many slices from the one on the left side all the way to that one all the way over there on the right side. So I integrate from left to right. But what I integrate is that S value, which is the distance in between the two curves. And for us, for this dx integration, we're always going to want that to be top minus bottom. So I integrate from the left to the right, but what I integrate is top minus bottom. Remember, that's the distance between the two, and if I accumulate the distance, it's going to give me the area in between the two. What's going to be hard for us is having this little paradigm shift, and instead of doing a dx integration, what if we had a dy integration instead? Now, a dx integration, if we think about it, right? If we pick like one little slice, like how about this slice, right? If we were to blow that slice up, it's really thin as far as its width, right? That one slice is really, really, really narrow as far as its width. And that infinitely thin width is what is called the dx. Now, if we were doing a dy integration, then instead of having the little vertical slices, which are infinitely thin as far as their widths, well, now we'd end up having these little rectangles that are really infinitely thin as far as their heights. So instead of having these vertical slices, which we have to accumulate from left to right, that's dx, now we're going to have all of these horizontal slices, starting with the first one at the bottom, and then the one above it, and then the one above it, right? We're going to want to accumulate all of these slices, starting from the bottom all the way to that top. But what we're going to be integrating again is the distance in between those 2 points, right? And we can think about that as s. But here for a dy integration, that's going to be off the screen, isn't it? Oh, well, that's right minus left, that's my s value. Just like how for the dx integration, we take top minus bottom. Because when we do top minus bottom, that gives us the distance in between. And if I integrate the distance in between, that's going to give me the area in between. But if I'm doing top minus bottom, I have to accumulate from left to right, right? That left slice all the way over there to the right slice. What's going to be harder for us, I think, is doing the dy integrations. If I have the horizontal slices, I'm going to have to accumulate them from the bottom up to the top. So I'm going to integrate from the bottom to the top. What I integrate is still the distance in between the two, but instead of doing top minus bottom, instead now that distance is going to be the right minus the left. Okay, so conceptually it's kind of the same whether we're doing dx or dy, but practically in how we work it out, of course, it's going to be different. But just think about it like this. If everything's kind of vertically oriented and we're doing a dx integration, the top is like the bigger value. Right? If we're thinking about the y-axis, up is positive, down is negative. Up, as things go up, they're larger. As things go down, they're smaller. So I take the bigger, the top, minus the smaller, the bottom, right? Top minus bottom, bigger minus smaller. That's going to give me the distance in between the two. That same logic applies for the dy. But if it's a dy, everything's kind of more horizontally shifted, horizontally kind of oriented. And I'd still want the distance in between the two. And when we're doing that subtraction, I would still want the bigger minus the smaller. But if we're thinking about the x-axis, bigger means it's going to be on the right. And then smaller means it's going to be on the left. So it's still big minus small. And then you integrate from the bottom to the top, or from the smaller value to the bigger value. But everything's just a little shifted. We are used to doing the dx integration. So those should probably be okay. The dy integration, we are not really accustomed to doing. But hopefully we will learn that it's really going to be the same type of calculus, just a little bit different. All right, dx integration, you integrate from the left to the right, but what you integrate is top minus bottom, because that's the distance in between the two. And if we add together all those infinitely many distances between the two, we get the area in between the two. Right? Integrate from left to right of top minus bottom for the dy integration. Now, sometimes I'll misspeak, and sometimes I'll say, hey, okay, right function minus left function. Some of these may not be functions, like that g curve, that's not a function because that would fail the vertical line test. That's okay, right? But we can still find the area between these things even if they're not functions. But for a dy integration, we are going to want to integrate from the bottom to the top. Now notice, since it's a dy integration, these things, right, that's y equals c to y equals d. The differential tells you what variables the c and d are. So it's from the bottom to the top, but what I integrate is the right minus the left. I take the bigger curve minus the smaller curve, because right minus left, that's going to give us the distance in between the two curves. And if I accumulate all of the distance in between the curves, that's how I get the area in between. The dy integration is going to take some practice, but everything's just going to be in terms of y instead of x. The limits for your integral are going to be y values. You're going to have y's in your equations, in your expressions for those curves, and of course your differential is going to be a dy. Everything's defined by the variable y for dy integration. Everything is defined by x, x equals a, x equals b. All these functions have x's in them for a dx integration. We got to be able to do both, so that way no matter what the AP exam tries to throw at us, we'll be ready. All right, let's go through and do these examples. Here we go. First one, it says, find the area bounded by the following graphs. says draw a figure and then shade the bounded region. All right, let's do this example A first. I always like to sketch the graphs. And sketching the graph is just going to help us kind of see what in the heck is going on. All right, so let's sketch it. We got that one, 3 minus x squared. That's a parabola. It's going to open down, but it's shifted up. So let's see. 1, 2, 3. It's going to be something kind of sort of like this. It doesn't have to be super precise, but that's more or less what that function is going to look like. And then the other one, we'll do it in blue. And so here we go. It's got a slope of -1 and an intercept of 1. So let's see, the intercept is going to be here, slope, I don't know. So something more or less like this. Okay, so we've got those two things graphed. Very good. So I can see that, yes, I do in fact have this region in between the two. And then we kind of have to decide whether we want to do a dx integral or whether we want to do a dy integral. Remember, dx is going to be vertical, dy is going to be the horizontal slices. And if we're doing dx, we'd be looking for top minus bottom. So if one thing is always on the top and the other thing is always on the bottom, that's kind of leading us to a dx integration. And then for the dy, we would want something to be on the right and then the other something to be on the left, because we want right minus left. We generally don't want the same thing on the top and bottom or the same thing on the right and the left. So let's think about this setup, and let's kind of visualize what a dy integration would look like. I would do the horizontal slices from the bottom all the way to the top, and for a lot of those slices, it wouldn't matter because the green is on the right and the blue is on the left. But up here near the top, notice the green would be both the right and the left. It is possible for you to do that integration. It's just harder. We're going to learn how to do it in a couple of class periods, but it's possible to do it. But since the green is the right and the left, that's not what I crave, right? That's not really what I desire. So I'm going to think, okay, maybe not a dy integration. Let's check dx. Is one thing always on the top, and then is the other thing always on the bottom? Let's see. No matter which vertical slice I draw for a dx integration, it looks like the green is always on the top, and the blue is always on the bottom. So here, the dx integration is shaping up to be a little bit better. Right, so we're going to do dx. We could do dy. It would just be a little bit harder. But since we're going to do dx, I need to know, like, what is this left intersection point going to be? And I need to know what is this right intersection. Because I have to integrate from the left to the right, and what I integrate is the top minus the bottom. All right, so let's go for it. We have decided that we want a dx integration. And so now I need to find what those intersection points are. So to do that, we're just algebraically going to take those two things and set them equal. So 3 minus x squared equals -x plus 1. Let's see, I'm going to get everything over to the right. So it's x squared minus x minus 2. And then we would want to factor it. And then let's see, I think that's going to be an x minus 2 plus 1, I think. X minus 2, x plus 1. Always check, right? FOIL it back together. It's going to work. And so here, set each factor equal to 0. We're going to get that the two solutions are -2 and 1. Let's go back to the diagram. Remember, your diagram may not be perfectly to scale. That's okay. Here, that left intersection point is -2. That right intersection point is 1. It may not look perfectly to scale. That's okay. But we found the intersection points, and now we're pretty much ready to go. Let's go for it. Here we go. This area of the region, we're going to integrate from the left to the right, so from -2 to 1. And what I integrate is the top minus the bottom. So let's set it up. The top curve was green, so that's 3 minus x squared. And then the bottom was -x plus 1. And then we just have to finish it, right? Top minus bottom, integrate from left to right. Ooh, that's definitely not a dy integration. It should have been dx. I'm glad I caught it. And so there we go. We're at top minus bottom. That's the distance in between the two. And if we integrate from left to right, we're accumulating the distance in between the two to get the area in between the two. All right, let's simplify this. Let's take this negative, and then let's distribute it. So distribute that sucker, and then let's see what we have. So we're going to have 3 minus x squared minus negative, so it's going to be plus x minus 1. And then let's combine, right? That and that are going to combine. And so I'm going to have this integration from -2 to 1. And I have -x squared plus x plus 2. Now, what I always like to do here is we actually have a little bit of a built-in check. This thing that we're about to integrate it should either match or be the -1 scale factor of the thing that we factored, right? And a lot of the times it's going to end up being the -1 scale factor, but it's kind of a nice little built-in check to make sure that I've distributed the negative right, and kind of haven't messed up with some of the algebra. The thing that we factor should either match or it's going to be off by a negative of the thing that we integrate. And here it's off by the negative, but I always like to have that little built-in check. Okay, very good. Now we could integrate it. So this one's going to be -1/3 x cubed, just the power rule, plus 1/2 x squared plus 2x. And then once we've integrated, then we would need to evaluate, which means plug in the upper number first. Remember, that was x equals 1, so we can plug that in for x. And then the lower one was x equals -2. We could plug that in for y, plug that in for x for the bottom integration. And then we'll be able to get this answer. Okay, I'm going to skip a little bit of the arithmetic just to kind of speed it up. But if you were to do that arithmetic, plug in x for 1, and then plug in the -2 for the x for the lower, and then do top minus the bottom, right, the upper evaluation minus the lower evaluation. If you were to finish all the rest of that arithmetic, you would end up getting 4.5, or 9/2. And you could check it if you have a calculator. Remember, the calculator can do this thing called Math 9. It's really wonderful. You could check it. You could do Math 9 with your graphing data calculator, and that should give you the same answer. And that's a good way to check. We should be able to do stuff like this by hand. Again, I'm going to save us all the time. I don't want to just grind out these videos and make it longer by just doing all the arithmetic. But again, we could have taken the 1, plugged it in for x, gotten the upper evaluation, and then taken the 2, the -2, plugged it in, gotten the lower, and then we could have done that stuff. I'm just skipping that for the sake of time so that these videos aren't extra long. But you should be able to do that arithmetic and then end up getting to that answer, which is 9/2, aka 4.5. And that is your geometric area of the region in between the two. Okay, now a really quick thing that we're going to talk about, and then we'll move on. If for some reason, if I had taken the top and the bottom, and if I had them switched, so if I did it, oopsies, and maybe I just never did the graph, and maybe I just guessed which one's on top, which one's on bottom, and maybe I guessed wrong. So if I had the top and the bottom switched, the only thing that's going to end up being off is that everything is off by a negative. So everything would be off by negative, everything is off by negative. So if you switched the top and the bottom and accidentally had them in the incorrect order, you would get the negative version of the answer. And that's a problem because really we're only looking at geometric area here, the area between one curve and the x-axis. The area of one curve could be positive or it could be negative based on whether that area is mostly above or mostly below. But if we're looking at the area between two curves, that's a geometric area, and that should only ever be positive. Okay, so if you somehow work a question, and if you get a negative, what that's indicating to you is that you have the top and the bottom switched. You don't necessarily have to rework the whole question. What you could do is just fix it at the end. Like you could do something like this. Okay, I'm going to cancel the negative, and I'm going to say, hey, it's not negative. It should be positive. And then you should write something like, I swapped top and bottom. And I'm like, oh, sad face. But you know, if you fix it, right, the negative is a mistake, but if you fix it by just crossing it off, and then if your answer is the positive, like that's fine. You don't necessarily have to go back and rework it, but you should know that, like, hey, that negative is the reason why it came up is because you have the top and the bottom switched. And so you can just fix it at the end, right? Just cross off the negative and be like, hey, I'm crossing off this negative because I know it doesn't make sense. It shouldn't be negative. And the reason why it's negative is because I made it oopsies. And I'm fixing the oopsies now by just crossing off the negative. You don't necessarily have to go back and rework everything. Okay, if you somehow get a negative answer, you shouldn't. You don't necessarily have to rework everything. Just cross it off and write a little note explaining what you did, right? If you just cross it off and then you don't write the note, it just looks like you're doing witchcraft. it's okay to cross it off and to kind of just fix it at the end, but you should write a little note demonstrating that you really know and you understand what's wrong and why you're fixing it. Right? So cross off the negative if you need to at the end, and then write the little note. Shouldn't be negative, should be positive, and then I'm fixing it now to make up for my earlier mistake of swapping the top and the bottom. Write that little note. You don't have to necessarily rework the whole question. Alrighty, so that's good. That's the first one. Let's go look at this next example. And here it's got 5 minus x equals 5 minus y squared, and then it's got x equals y plus 1. Okay, we're not really used to dealing with x equals and y equals. X equals for our curves. Well, that's okay, right? We can still graph it. Let's do the one on the right first, because this one's going to be easier. You could just solve that one, right? That one would be y equals x plus 1. That one would be really easy for you to switch and solve for y. And so that one's going to look, it's going to have a y-intercept here, a slope of 1. So it's going to look more or less kind of sort of like that. Okay, so that one's done. Good. Now, the other curve is like a little bit harder. Let's think about like what it would have been if the mirrors were swapped. If I had something like this, y equals 5 minus x squared, what type of curve would that be? Well, it's quadratic, so it's going to be a parabola, but it's negative, so it's going to open in the negative direction, and it's shifted positive. So it's going to be shifted up, but it's going to open down. And so that one would look like that. It's shifted in the positive direction because the constant is positive, but it's going to open in the negative direction because the x squared, the quadratic part, is negative. So that's great. Let's kind of apply that same logic to x equals 5 minus y squared. It's also going to be a parabola, but it's going to be a horizontal parabola. Right? The y equals yada, 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 x squared, that's a vertical parabola. It could open up or down. It could be shifted right up or down also. But the x equals yada, yada with the y squared, that's going to be a horizontal parabola, either opening to the right or opening to the left, and of course could be shifted also. Here, it's going to open in the negative direction, which for us is to the left, but it's shifted in the positive direction. So that one's going to be shifted. 1, 2, 3, 4, 5, shifted 5 to the right, but then it's going to open to the left. And then that graph is going to look something sort of like this. Right? Again, it may not be perfectly to scale, like my drawing skills aren't super wonderful, but it should look generally something like that. Right? It's a parabola, but it's a little bit weirder for us to graph because we're not used to doing x equals, but it's still okay. Okay, if you wanted to solve it, you could, let's see, we'd have y squared is equal to 5 minus x, so we would have y is equal to, here's the mistake that a lot of people would do. They take the square root and they only have the positive. Okay, if they had the positive square root of 5 minus x, the positive part, I'll do the positive part would be here. It would be that part of the horizontal parabola, but really, if we physically reduce it from quadratic to linear, we would want the plus or minus, and the negative part would be this corresponding bottom part of the parabola. We want the whole parabola. So if we solved it for y, we would get plus or minus that square root of 5 minus x. And we know what the square graph looks like. It's got the horizontal reflection. So you should be able to graph those two y equals, but you'd want them both. Top part, positive root of 5 minus x, positive root of 5 minus x, and then the negative root of 5 minus x. That would be the bottom part. We have that horizontally opening parabola. Shifted to the right, opens to the left. Okay, so now we've got this region between. That's good. Let's think about dx integration or dy integration. And dx would be top minus bottom, and that would be fine for a while, but then over here, we'd have the same thing on the top and on the bottom. And while that's able to be done, we would generally prefer that not to be the case. So dx integration isn't looking so spectacular. Let's think about a dy integration, though. Is there always one thing on the right and then a different thing? These aren't functions. Well, the blue one is, the green one's not. Is there always one of the graphs on the right and then the other on the left? Yes. So this is actually set up pretty well for a dy integral. And that's why you started with x equals. It was x equals, and then those things were defined by y, because it's really leading us to a dy integration where we have the right minus the left, right? And that distance in between the two is going to be the right minus the left. Okay, so here we go. We're going to need to find the intersection points. I need to know what is this bottom value. So I'm going to end up integrating from that bottom value up to the top one. And then what I'm integrating is right minus left. So let's go set these things equal and let's go find the intersections. Here we go. 5 minus y squared equals y minus 1. Let's add everything over to the right. Y squared plus y minus 6. I think that's a plus 3 minus 2. So then y is going to be negative 3 and then positive 2. Okay, so if you have to find the intersection points, so be it. If you have a calculator, graph them, find the intersection points, but you really should be able to do that by hand. I kind of messed that up. Oops. There we go. Let's fix it. So this bottom one is at negative 3, that top one's at 2, and we have to accumulate all of those slices. Remember, each slice is right minus left, but we're going to accumulate them from the bottom up to the top. All right, here we go. Let's do this one. Here we go. Our area, we're going to integrate it from the bottom to the top. What we integrate, though, is going to be the right minus the left. And this was a dy integration, so that's y equals negative 3. That was y equals 2. And then both of those curves had better be in terms of y. So the green one, that was the one that was on the right. So that's the one that comes first. 5 minus y squared. And then the blue one, that was the one that was on the left. So I got it set up. Integration from the bottom to the top of the right minus the left. And now let's kind of just take this negative and let's distribute it again. And then let's see what that integration is going to boil down to. We've got 5 minus y squared minus y plus 1. So we've got negative 3 to 2. And then it's going to end up being a negative y squared minus y. 5 and 1 is 6. And remember, we have that little built-in check, and this is still going to be true. This should either match exactly the thing that we factored, or it's all going to be off by that negative 1 scale factor. And a lot of the times, it does seem to be off by that negative 1 scale factor. Okay, so that's good. We got that built-in check. Now we would integrate it. So it's going to be a negative 1/3 y cubed. We're just integrating with respect to y. So negative 1/3 y cubed minus 1/2 y squared plus 6y, not 6x, 6y. And then we'd be evaluating it from y equals negative 3 to y equals 2, right? You don't have to write the y equals, but that's what the evaluation bar means, right? Plug it in, but that differential at the end kind of tells you what the variables were. That was y equals negative 3, y equals 2. Again, I'm going to kind of skip this arithmetic. We would plug in the 2, right? That's from changing the y's to 2's. Then we would do all that work, changing the y's to negative 3. We could do that. I'm going to skip it just for the sake of time. And then this answer would end up being 125 over 6. Could I do that by hand? Yes. Should you also be able to do that by hand? Yes, right? You should be able to do that. I'm skipping it just for the sake of time. And remember, we could have always just used the calculator, right? Your graphing data calculator could also Math9 it. Now, just because it's a dy integration, that's okay. Remember, your calculator, the x is just your variable button. So when you type it into the calculator, you will have to use the x button instead of y. So that's okay, right? X is just your variable. You have negative variable squared minus variable plus 6, and you would Math9 that variable from that variable being negative 3 to that variable being 2, and then, of course, you would define it with that variable. Whether it's x, y, z, element OP, it doesn't matter. You just always use x when you're typing it into the calculator, but you could use Math9 to check. You should be able to do these computations by hand, but we could always use the calculator, the Math9, to check. All right, that's halfway through the notes. Let's flip it over and let's do the next page. Hopefully this is recording because I don't want to have to do this again. That would make me very sad. All right, there it is. All right, next one, here we go. We've got x equals, or f of x equals x to the 6th power, and then g of x is x plus 2. Let's graph them. Here we go. We got x to the 6th. It's going to look kind of like a parabola, just a little bit flatter, and then it gets a little bit steeper. A little bit flatter, a little bit steeper. All those even power functions look mostly like a parabola, just a little bit flatter around the origin, and then they get steeper depending on the exponent. and then x plus 2. Okay, so that's going to be 1, 2 units, a slope of 1. I don't know, more or less something like this. Okay, so there is the G curve, and the F was in pink. So we could, first thing we need to do is decide, do we want to do dx or do we want to do dy? And this one is setting up better for a dx integration. A, because the things are defined by x's, but then also, if I were to do a dy, sometimes the pink would be both the right and the left. And while that's manageable, it's harder. But the dx integration, the purple is always on the top, and then the pink is always on the bottom. So here the dx is the way that we want to go. Functions are set up for it since it's y equals, and then it's defined by x. And since there's always one on top, one on bottom, the dx integration is the better of the two. So here we go. This area, we're going to have the integration. I'm going to need to figure out what these two intersection points are. We're going to integrate from the left to the right. But what I integrate, it's going to be the top, which is purple, minus the bottom, which was in pink. And this was a dx. Now, to find the intersection points, typically you would take those things and you would set them equal to each other. But that's not something we're going to be able to do by hand, right? We can't solve 6-degree things by hand unless it's like really easy, like just x to the 6 equals, I don't know, like 256 or something like that. If it's like a really easy and even thing to take a 6th root of. But here we've got the extra x, so that's a problem. So we wouldn't be able to do that by hand, but we could still use the calculator, right? We can still use the calculator to go find those intersection points, and then we're going to be good, right? So we couldn't do it by hand. That's okay. We're just going to use the calculator. The left intersection point ends up being really nice. The left intersection point is at -1, and then this right intersection point, it's a little bit harder. Right? We get -1, and then the one on the right is 1.2148623, and I'm assuming that decimal probably keeps going. Now we're going to want to store that decimal because it's going to be about like 1.214, but I don't want to use a rounded solution. I want to use that exact stored value. Okay, so I know the -1 was exact. That was nice. And then the top one was the 1.214, yada, yada, yada. But I'm going to use the stored version. So I've used the calculator to find the intersection point. And then when my cursor was sitting on that point, right, I would quit out of the graph, and I would hit stow alpha A. And I would store that number. And then when I do the integration, I'm just going to integrate it from -1 to alpha A. Now, you don't really need those parentheses. If you want to, you could drop them. So we've got -1, 1.214, or whatever, right? That was my alpha A. If you wanted to drop the parentheses, you could. We would have x plus 2 minus x to the 6 is really nothing to distribute since it was only one term. And so there we go, right? And if you want to put those parentheses, that's okay. But then we would be able, the integration would be fine, right? Because the integration would be 1/2 x squared plus 2x minus 1/7 x to the 7th. The problem wouldn't be the integration, nor would the problem be plugging in -1. The problem would be plugging in this really ugly number, right? Taking this and then plugging it in for x. That's going to be ugly. Okay, so you wouldn't have to do this. This would be a calculator question. So then we would just use our graphing data calculator. We would use the Math9 feature of it, and we're going to end up finding that the area bounded by these two graphs, right, the area of that region, is 3.967. Okay, so we integrated from the left to the right, but what we integrated was the top minus the bottom. Very good. Let's move it on. Get near the end. Next example kind of helps us explain, okay, well, what happens, Mr. Bell, if the functions cross over? What if we have G, and then what if we have, so I'll do G with the orange, and then here we go, Broncos colors, I'll do the F with the blue. Okay, so what if sometimes G is on top and then F is on bottom, and then what if they switch and sometimes F is now on top, right? And we're going to try to be finding the areas of these regions, right? There's this region right here, and then there's this other region. What if I wanted to find the area of both of those regions combined, right? What's the total area of those regions? Well, really, we'd want to think about, okay, well, this one's like region 1, and then that one's like region 2. If you want to, you could just kind of split it up, right? I don't know what these intersection points are. Let's call that x equals A. Let's call this one x equals b, and then we'll call this one over here x equals c. We're not going to care about to the left, and we're not going to care about to the right, right? Those unbounded regions, we're not going to care. We want the area between the two that's bounded by the two, so the sections kind of over on the sides, they don't matter. But if we were looking at this region 1, right, I know I'd want 1 plus 2, that would be the total region. But for the region 1, I would integrate from the left to the right, but what I would integrate is g minus f, because for that region 1, g is the function that's on top, f is the function that's on the bottom. So I would do g of x minus f of x. And then that integration would give us the area of region 1. And then I would have to add it to, and then this would be the integration from b to c. And then for the integration of the second one, it's also going to be dx. But now for the second one, now the blue, now f is the curve that's on top. So now I would need to do f minus g. So if the functions cross over each other, and if they kind of change places, and if sometimes one is on top and other times a different is on top, just break it up and just do different sections for different regions, and then just add all those respective pieces together. That's probably the easiest way to do it, and especially if you do not have a calculator, that's the way that you would want to do it. Split it up, find the area of each piece, and then just add them together. Remember, each piece. For dx, you'd integrate from the left to the right. So here's our first integration from a to b, second one b to c. But what you're integrating is top minus bottom. You could also do dy's, but that wouldn't look very pretty here. If you wanted to, and if you had a calculator, it would also work like this. I could just go from a to c, and then let's say, it doesn't matter. I could pick f of x minus g of x, or I could do g of x minus f of x, right? If I wanted to, I could do one of those two, but I would need to take the absolute value first. If I took the absolute value, well then the order for the subtraction doesn't matter, right? Because when I'm doing subtraction, if I did bigger minus smaller, that means I'm going to end up with that positive distance between the two. But if I for somehow had the subtraction where the smaller term was first and then the bigger term was subtracted from it, if I did small minus big, the answer would be negative. But if we took the absolute value, it would kill the negative. So if I took the absolute value before I integrated, it really wouldn't matter whether f or g is on top or whether they switch. Since that would give us the total area of that region, you could, right? But you really wouldn't want to do the absolute value unless you had a calculator. I think splitting it up, finding the individual pieces and adding them together, that's easier. But it is possible to just do the absolute value first and then integrate. And then if you have the absolute value, the order for the subtraction doesn't matter because at worst it's off by a negative, but then the absolute value kills the negative anyways. All right, so the absolute value would also work, but I would suggest splitting it up and just doing each region individually. All right, here we go. Last one, and we're going to actually work this one out. We're going to do it two different ways. We are going to find the area of this region two different ways. We're going to do it with dx's, so that'll be the method 1, and then we'll also do it with dy. So we'll do work it with y's. Okay, so let's see. It says find the area of the region bounded by the graphs. We got y equals x squared. Let's graph it. Y equals x squared. That's this one. Okay, so that one's good. And then we have the line 18 minus 3x. Here we go. And then it says the x-axis. Okay, that's easy. Yeah, I guess we can see the yellow sometimes. So the first thing is always deciding what region do we want. It's not the region over here. It's not the region over there. It's not up there, right? What region is bounded by those three things? What region is bounded by the red and the orange and the yellow? It's going to be just that one kind of in the bottom. Right? So always make sure you have the right section first. Right? This is the region that we're going to try to find the area of. Right? And we're going to do it two different ways, with x and with dy. Alrighty, let's do the dx first. Remember, for dx, we're going to want to integrate from the left to the right. and then we're going to integrate top minus bottom. But we're going to want to split this one up, right? Because for dx, we have these vertical slices, and kind of right around here, it's going to swap. Because for that left section, red is on top, yellow is on bottom. But then for this second part, now orange is on top. So I'm going to have to split this up, and we're going to integrate. That's at 0. So we'll integrate from 0 to 3, 0 to 3, and then in that case, red is on top. So that's going to be x squared minus, and then the yellow was on the bottom, so that's just 0. By the way, do you need to write minus 0? No, right? You don't need to write minus 0. So I'm just going to have just the red one. So we're integrating x squared. That's going to give us the area bounded by the red and the x-axis. And then that one's over here at 6. Then we'll integrate from 3 to 6. And then I would take the orange minus the yellow. But again, the yellow is 0. So I just need the orange. And then that one is 18 minus 3x. So here dx would be pretty easy. You have to split it up because the orange and the red, they each take a turn being on top. And so we have to split it up. Not super difficult though. All right, let's do this one. Here we go. 1/3 x cubed. That one's going to get evaluated from 0 to 3. The next one would be 18x minus 3 over 2 x squared. That one's going to be evaluated from 3 to 6. And then let's finish it. Here we go. We're going to plug in 3. 3 to the third power is 27. 27 divided by 3 is 9. So there's the upper evaluation minus the lower evaluation. That was really nice. Lower one, 0. Doesn't matter. And then we have the second piece. Let's see if I plug in 6. 18 times 6. That's 108, I think. Yeah, 108. And then minus 6 squared would be 36. 36 times 3, actually 36 divided by 2 would be 18. 18 times 3 is 54. Okay, so there we go. So if I took 6 and plugged it in, 18 times 6 is 108. And then 6 squared, 36 divided by 2 is 18. 18 times 3 is 54. So there's the upper valuation minus the lower valuation. Here we go. 18 times 3, okay, that's 54. And then minus, if I plug in 3, 3 squared would be 9. 9 times 3 is 27. So I'm going to have 27 over 2. Whew, okay, that was a little bit of arithmetic. Oh well, let's finish it. We have the 9 plus, let's see, we have 108. But then I'm going to minus 54, minus 54. All those are going to cancel, so that's really nice. So really, I'm going to end up having the 9. The 9 is still there. And then I have the minus, actually distribute that, so minus negative 9 plus 27 over 2. And if it was a free response question, you know, that would actually be a perfectly good stopping point. Right? 9 plus 27 over 2, that's fine. You don't necessarily have to get it all the way down to this final singular answer. But 9 would be the same thing as 18 over 2. 18 plus 27, that's 45. So if it was a multiple choice question, you would have to probably get it all the way to that answer. But if it was a free response, you would have been safe to stop earlier. Now, let's do this same region. We're not going to change the curves. We're not going to change the intersection points. Let's do the same region, but let's do it with the dy integration. Okay, now for a dy integration, we're going to integrate from the bottom all the way up to the top. And here we're only going to need one integral because the orange is always on the right, and then the red is always on the left. And we're going to integrate from the bottom, which is 0, up to the top. Okay, so here we go. Let's go for it. Yeah, we'll kind of do it here. We'll integrate it from the bottom, which is y equals 0, to the top. And then what I'm going to integrate is the right minus the left. Okay, but I need to get those right and the left curves. I need to get them in terms of y. So let's go solve for them. Right? The red one was y equals x squared. That means x is going to be plus or minus the root of y. All right, so this red parabola right here, you could write it as x equals plus or minus the root of y. The x equals negative root, that would be the left side, which we don't really care about. Oh, what is it doing? No, don't do that. The left side we don't care about. So there's the left curve. It's the root of y. You have to go solve for it, right? Take that equation, solve for y. Not super difficult. And then the other one is just algebra, right? Add the 3x. So we're going to have 18 minus y. That's 3x. So therefore, x is going to be 6 minus 1/3 y. So we have to take these things and solve for the other variables. 6 minus 1/3 y. That would be the equation for this orange curve, but in terms of y, right? Solve it for x to get it in terms of y. You have to do a little bit of work, but now we're going to be able to do this interval. I'm going to pick it up right here. So let's integrate. 6 with the integration of dy, that's going to be 6y. And then here I have 1/3, but if I add 1 to the exponent, it's going to be y squared divided by 2, so it's going to be 1/6 y squared. And then that's y to the 1/2 power. So if I add 1 to that exponent, it's going to be 3/2, which means it's going to kick out a 2/3. And then it was negative. Oops, that's too far over. So there's the integration. And then we have to evaluate it from y equals 9 and then subtract y equals 0. So let's plug in 9. 6 times 9, that's 54, minus, okay, 9 squared is 81, so I'm going to have 81 over 6. Come on, smartboard, you're really frustrating me today. 81 over 6, and then minus, let's see what this last one's going to be. 9, and then squared would be 3. 3 cubed would be 27. 27 divided by 3 would be 9. 9 times 2 is 18. Okay, so all that piece ends up being 18. So there's the upper evaluation. I guess I should do this, right? There's the upper evaluation, and then your lower evaluation. All right, plug in 0, everything's going to be 0. That's really lovely. So we're going to end up finding that this area, we'll kick it up here, the area is 54 minus, those are both divisible by 2, so I'm going to actually divisible by 3. So that's going to be 27 over 2. So minus 27 over 2, minus 18. Actually, let's combine the 18. Right, let's combine the 54 and the 18. Might as well. 54 minus 18. That's smelling like a 36. So here we go. If we wanted to kind of leave this 36 minus 27 over 2, that would be a perfectly good free response answer. There wouldn't be anything wrong with it. Really, if you could have left it a couple different ways. You could have left it as like the 54 minus the 81 over 6, and then minus. You could have left that other one over 3 also. You didn't necessarily have to reduce it. But yeah, that would be a safe stopping point. There's other things you could have also gotten and been equally correct with. But that would be a perfectly good answer. Now let's go a little bit farther. That's 72 over 2. 72 minus 27. Oh, would you look at that? That's the same 45 over 2 that we did, that we got earlier. So whether we do the area with x's or whether we do the area with y's, right? The dx integral versus the dy integral. Does it ultimately matter? No. It's the same curves. It's the same region bounded by them. And so, of course, it's going to be the same area. Now, how you find it, of course, is going to create some differences along the way. Like here, we built it with doing dx's, which means we were accumulating all those little vertical slices, top minus bottom, from the left to the right. And then here we had the horizontal slices. And then we accumulated them right minus left, all the way from the bottom to the top. So the process is different, right? If you were to compare the two integrals that you set up, those are different. How you integrate them, right? The actual calculus that you do, that's different. Even if you were to look at kind of this second to last step, they look different. 9 plus 27 over 2 looks different than 36 minus 27 over 2. But if we were to all get to the same final singular answer, would we get the same answer at the end? 45 over 2, 45 over 2, yes. So it's kind of a little bit weird. dx or dy, it's ultimately not going to make a huge difference. The setup's going to be different. The work that you do in the middle is going to be different. Even that second to last step, in all likelihood, is going to be different. But you should get the same answer, regardless of if you do x's or if you do y's, because it's the same region, bounded by those same curves. How you build it from left to right, of right top minus bottom, or from bottom to top, of right minus left, how you build it doesn't matter. It's that same area. Right, so the dy integration is probably going to be a little bit hard for you at first because you're not used to doing it. But ultimately, I hope that you guys find that it's really not that much difference. It's a little bit more annoying, but ultimately it's about the same level of calculus. All right, thank you guys for watching. I know this was a little bit long. Hopefully it was okay. I did shave off some of the arithmetic, skipping some stuff in the first couple of questions. But I wanted to do this one to point out that even those second to the last steps, even these may not look like they're the same, but the final singular answers, they will match.